All right, here's your next homework assignment. I'll put it up in World Class 2. So same section as homework 3.
Oh, great.
But we're gonna make this due Monday, and let's really try to make that happen. Does that sound okay? Because I feel like I wanna have exam 1 before the break. And this would probably be the last big homework before that, and then I'll give you homeworks that'll like prep you for the exam and stuff. Don't stress about the exam. I know that if you've had me before, which most of you had, my exams are not where the suffering.
I was curious if you're thinking take home or
No, we're gonna do an in class, certainly for the midterm, because I want you to remember some things, you know, like remembering that we have a quiz today, which I finally just remembered just right now. So we are gonna do a tiny quiz at the end of the hour.
Wait, the quiz was supposed to be last Wednesday.
Right, but no one reminded me.
I reminded you at the start of class.
But then you didn't keep reminding me.
I'm not that person. I'm not that person.
You think that was good enough? Are you kidding me? No. So.
I refuse to be that person.
You refuse to take the quiz?
No, I refuse to be the person that's like, you forgot the quiz.
No, it's all right. Like on the way out, it was like Christian and Kayla, or one of the two of them said, "So how about that quiz?" I think it was you, maybe. Yeah. So we gonna do that quiz?
This is awesome because all of it left my mind over the weekend. So.
What's a group?
It's a set G. Using the law of composition.
Got a composite, got like some kind of operation.
Yeah,
Okay.
provided that it's associative.
Associative.
It has an identity element.
Identity.
And it has inverse element.
Inverse.
And it's closed.
And closure under the operation. Sounds like you're ready for at least that part of the quiz.
I got 1 out of 5.
Don't worry, it won't be bad. By the end of the class, you'll have reviewed everything that could possibly be on there anyway. All right, let's see, where are we going? Whoa, yes. I don't think we're gonna talk about that. We're just gonna jump right into subgroups. It's like a group that's a subgroup of another group. It's just like that. It's just like you think. So suppose G with some operation is a group. If H is a subset of G and H is a group itself under the operation dot, then we say H is a subgroup. Of G. And we write, and I've shown you this notation before, but we write, so it looks like less than. Contextually, you would know it isn't because you're doing algebra, but it does look like a less than, it looks like a subset, and sometimes people will use this notation to show that this has the potential of these being equal. Either one of these is great, they're fine. I don't even think our book uses this notation, I haven't seen it in there, but it's very, very standard and ubiquitous notation. So let's get a couple subgroups that we don't even need to know about G to know the following facts. We have trivial subgroups of any group G. So first off, if H is just equal to G, like the whole group itself is a subgroup of itself. That's dumb, but it's true. So the whole group itself can be thought of as a subgroup. One of the lamest subgroups because it's the whole damn thing. That's not very interesting. So this is the biggest and most boring, possibly, but you can get a little bit more boring because you could also just have the identity element from G. And that's the smallest. And in between those two, we might have an entire family of them. So this is the smallest trivial subgroup. And your Cayley table's pretty chill. It's that. So, nice. Completely owned. If H is a subgroup of G and H is definitely not all of G. So here I'm putting a slash through the equals part of subset to show it as a proper subset. So proper subset means it's not equal to, then H is a proper subgroup. And those are the ones of most interest to us. Just a little terminology there. So let's look at some examples because we've got a lot of groups under our belt so far. So if G is D3, what was D3? This is most of the quiz. No, I'm just kidding. No, I won't say that. What's D3?
That wasn't the dihedral group.
That's exactly it. Dihedral group. What was that? The dihedral group of a triangle.
Yeah.
The group of symmetries on the triangle. Yeah. So we're going to talk about this in a couple of ways. So this was D3 is the dihedral group, which is just a really awesome phrase, right? Like the word dihedral. Where else do you hear that? Do you hear that in like chemistry or something? Is that like a chem thing?
I think so.
Seems like a chem person thing. The dihedral group of a triangle, and that's all the symmetries. But we also looked at this in a different way. Remember how we mapped each of the symmetries to a permutation? So there's another name for this, which is S3, which is also the symmetric group, which is equal to the symmetric group on 3 objects. And that is just equal to all permutations of 3 things. So let's see if we can kind of recall how that all went. Had my little beautiful triangle here. Let's call the sides 1, 2, 3, like that. So let's think about what those permutations were. So first off, we have just the identity. And the identity takes the corners of the triangle and keeps them all the same. Let me stop and see if the notation, do you remember that as well? That is a permutation, looking okay? Because I'm reviewing stuff too, and we're gonna get deeper into it as well. So we had the identity. Don't move the triangle. What else can I do to the triangle?
Rotate it once counterclockwise.
Rotate it in 120 degrees a click. So if I rotate, let's call this row 1. We take 1, 2, 3. So if I rotate it, then the 1 goes to the 3, the 3 goes to the 2, and the 2 goes to the 1. Does that look sensible? Cool. And then we got row 2. And that is 1, 2, 3. So that is 2 clicks to the left, or I could just click it in the opposite direction to get the same thing. Do you see what I'm saying? So if we're thinking our rotations represent counterclockwise, then 2 of them would be one to the right. So in other words, one would go to two? Wait, am I saying that right?
Yeah, one goes where the two is.
Yeah, one goes where the two is, two goes where the three is, three goes where the one is. Let's check. Let's just check to make sure that this is two of these. So I'm gonna do row one composed with row one. And that is 1, 2, 3, 3, 1, 2, 1, 2, 3, 3, 1, 2. So how do I read these? And I start on the right side, right? We feed in this way, because these are functions. So we start from the right. 1 goes to 3, and 3 goes to 2. Looking good so far. 2 goes to 1, 1 goes to 3, and then this better be 1, but let's do sanity check. 3 goes to 2, 2 goes to 1. And sure enough, that actually is our row 2 over there. Yeah, cool. And then what other operation, what else can I do to this triangle?
You can flip it.
I can flip that sucker as well. So, getting my eraser or something, thanks, there it is, thanks my brain, I guess, thanks eyes for seeing things. We also have these flips. We'll call those tau just for the hell of it. Tau 1 is going to be that flip. So it just flips 1 and 2. Tau 2 will be, so this is tau 1, tau 2 will be that guy, and that's gonna flip 1 and 2. Oh wait, no, what did I say? I screwed it up, didn't I?
2 is supposed to be the same.
Yes, thank you, yeah, so the tau 1 just flips 1 and 3. Thanks. And tau 2 will now flip 1 and 2. And then tau 3 must keep 1 fixed and flip 2 and 3. Sound okay? So I've got, notice here, the order of the dihedral group is what? What does it mean? What's the order of a group?
The amount of subgroups
6,
that it
right?
has.
Too fancy. Just the number of things in it. That's an awesome number, but that's a different number. It's the number of elements in it.
So 6.
6. Now, I've talked about, I mentioned S3 here. It turns out that this thing D3 that we've just talked about creating in one way is also the same as the group of all permutations on 3 objects. If I have 3 things, 1, 2, and 3, so I've got 3 slots, I got 3 things. How many different ways are there to arrange 3 things in a row? 6. We have 6 of these. These are literally all the ways to take 3 things and rearrange them. So this S3 has 6 things in it, and it's also the number of things in D3. There's other dihedral groups. If you were to look at the dihedral group on a square, I'm not sure that it's S4, but we can take this, and I could think about what S4 is, just independent of all the triangle stuff. So S4 is the permutations of 4 objects. How many things are in that group? What's the order of S4? How'd you come up with 6? What was it?
Is it 24?
It's 24. Because you've got 4 ways to fill the first slot, then 3, then 2, then your last object is already determined. So there's S4. How many things are in S5? 120. These groups are starting to get really big. But these permutation groups are a very important class of groups. And in fact, let's just get the general format up here. If I say S sub n, this is the symmetric group So in some ways, I'm actually giving us another group example, or like a whole class of them. Symmetric group on n objects. And this is just equal to the collection of all permutations of n things. All these things, this is a group that we have in line. So I kind of pushed that idea forward a bit. What are some subgroups of S3? Let's come back here. I kind of just wanted to push this general idea so we have that terminology. But what are some subgroups of S3? What are some little subsets of, and think in terms of maybe the geometry of it, that might be a little easier. Yeah, what do you
One
think?
of the subsets rotation and one of the subsets flipping it.
Yeah, so the rotations, just the group of rotations is a group to itself, or the collection of rotations. So the first one would be, we've got our identity, because I need that for a group, and then I've got row 1, and I've got row 2. And this is a subgroup of S3. It's also a subgroup of D3, because they're the same damn thing afterwards, or they are the same thing, just notational difference. So you could even make a Cayley table if you wanted, but it's not super informative. What's the operation? Composition, yes, so composition. So the identity stuff is pretty boring, always. And what's row 1, row 1? Row 2, what's row 2, row 1? Or row 1, row 2? Identity, because that gets you 360 degrees. You can do that in either order. What's row 4, row 4? Row 2, thank you, yes. row 2 is row 1. Yeah.
Would also be row 1.
But it would, you're right, yes, indeed. I don't know where I was coming up with 4. So we got a little Cayley table. What's another subgroup?
Tau.
Tau?
ID.
ID, Tau? And what were you gonna say, Cormac?
Just do row 1 and ID.
Ooh, I like that. Let's check. So before we go to that one, can I just do ID and row 1? And let's answer this together. So Cormac's posed a question, is that a subgroup? Why do you say no now?
Because I think R1 composed with R1 would be R2, which is not in your group.
This isn't closed. Yeah, so very good. Because row 1, composed with row 1, is row 2, and that's not in this set. So I would have to add it to get completion. So now it's a subgroup. And then Sophie was tossing out, so here's subgroup 1 of that. Sophie, you said identity and all these guys, or just, what were you thinking?
Well, I don't know, because I know that sometimes when you're doing taus, well, in this situation, it would be a tau, you can wind up with the rotation, so I don't know what combination of the taus and rows you would need for this subgroup.
Yeah, it started to feel, how about if I just close it, is that okay?
No,
How come? So tell me why.
because if you, oh, I guess, no, yeah, because if you do tau 1 and tau 1, you're back to the identity, so yeah, that's
Yeah.
closed.
So that's closed. So just this. So this is a subgroup. What's another subgroup? Can you give me 2 more?
Tau 2 and Tau 3.
Yeah, perfect. Exactly. So these are all subgroups. Let's answer that question that Sophie and I were chatting about. What if I did try to like mix it up? So I've got identity, tau 1, and tau 2. Let's just do the composition using these formulas over here, right? We've got exactly the information we need to compute that. So let's do tau 1, tau 2. So that means I'm just gonna copy it down. So 1, 2, 3, 3, 2, 1. remember I do tau 2 first. Tau 2 says 1 goes to 2, and then 2 goes to 2. 2 goes to 1, 1 goes to 3. Looking a little grim. And then 3 goes to 3, but then 3 goes to 1 from that guy.
That gives you row 2, and that's not a.
And that's a rotation. So the composition of any two flips, we could surmise is not back in there. So as soon as I put tau 2 in, then I've got to add in a rotation. Whatever rotation that was. Was it 1 or was it 2? It was 2, thanks. Kayla's always like doing secret help to me. She's like, don't axe that, buddy. Kind of, a little bit, keeping me on the level. So as soon as I start this, I end up having to you will have to add everything. Because then you have to think about the composition of this and this, and eventually you'll end up getting the whole damn group. So what we have is just this, and that. So we can make a little tree of subgroups. So here we've got S3 at the top, and at the bottom we've just got identity. So these are the trivial subgroups. Everything, basically just the identity. And then inside here, notice there's no nesting. It's not like one of these is nested in the other. So we're just gonna have these little subgroups listed across in the middle here. We've got our flips. ID, tau 2, and I'm gonna take these commas out, and then ID tau 3. And the way you kind of wanna do these is like this. And you make this little tree structure, or kind of like the bones of the group. And once we get a little bit more interesting groups, there will be multiple layers of nesting in this, but that's about as good as we can do right now. Let's talk about another group that we haven't really even talked about. So it's kind of new group day, but also idea day. So let's take a look at, here's a new group. And it is the complex numbers minus 0. So that we call C star in our book. The complex numbers take out the 0 point. And then our operation is multiplication. And so I've got now the complex plane taking out the origin. So here's my real axis, here's my imaginary axis, and everything in there is a complex number in the form a plus bi. Should we talk about the complex numbers? Has it been a while, or we feel okay about that? Feel okay? And what's I squared? I think we should talk about the complex numbers. Okay. that was like my little litmus paper there, right? Like, where are we at on this? So the complex numbers all form around this number I that we can think of as the square root of -1. And to multiply, to think of two complex numbers, or a complex number, you just visualize the plane. The vertical axis is the imaginary component, the horizontal axis is the real component. So if I said to you, hey, I've got -1 plus 2i, that would be -1 on the real axis. You can kind of think of this as the point -1, 2. So like this, you can kind of think of it as the point A comma B in the plane. So it's -1, 2, and that is my complex number right there. When I multiply two complex numbers, I just FOIL them. And so FOIL, again, FOIL, what doesn't it do? At every level of mathematics, FOIL exists. So first times first, A times C, outer is ADI, inner is BCI, and then the last is BDI squared. But I squared is -1. So this actually turns into AC minus BD plus the imaginary part is AD plus BC times I. So if you have to multiply two complex numbers, FOIL them out. Just remember that I squared is replaced with -1. Notice that this is just another complex number inside there. As long as they're not both 0, this will not be 0. So we have closure under multiplication. We would like to have an identity. What do you think the identity is? Let's try it. So if I take I times I should get I back. But I don't get I back. No. 1. It's so much simpler. Yeah, it's just 1. Because we're multiplying. So our multiplicative identity is just 1. So we have closure, check, identity equals just the number 1. 1 times anything, just get you 1. You could replace this B with a 0 and this A with a 1 and see that it all works out as an identity. In terms of inverses, we've got, so if I have A plus BI inverse, that turns into A minus BI over A squared plus B squared. So let me prove that to you with an example. And actually you would break it into real and imaginary parts. Minus B over A squared plus B squared I. So for example, if I asked what is 1 plus 2I inverse, according to my formula, it should be 1 over 5 minus 2 over 5 I. So that means that I should be able to check this out then, so I'm going to check. Take 1 plus 2I times 1/5 minus 2/5 I. FOIL, right? FOIL again, 1/5 on the F. The outers minus 2/5 I. The inners plus 2/5 I. And the last is minus 4/5 I squared. But since I squared is -1, that's plus 4/5, and we just get 1. So I kind of went fast through that. But it's just multiplying numbers and keeping an eye out for I squareds. So this is a group, and we have associativity because complex numbers, multiplication is associative. You can do it in any order. I'm not going to prove that. You don't want to see me prove that. No one wants to see that proved, ever. So we've got this new group that we can play with. Let me show you a cool subgroup. So if you kind of had part of a subgroup. So a subgroup of C star multiplication is 1, minus 1, I, and minus I. That's a subgroup. Let's check it. Times 1 minus 1, I minus I, 1 minus 1, I minus I. I gotta go pee. Could you fill in that Kaylee table for me? Thanks. soothing little table, right? Nothing too crazy here. One, and then minus I. Oh, and it's nice and symmetric too, because this should be in abelian. Well, the original group is abelian, so its subgroup is gonna be abelian, commutative. Gosh, I'm just cheating now. Now I'm like, what didn't I put in that row? I'm being so lazy, I can't even multiply -1 times something. So then that's -1, and then that must be 1. And then that must be minus I, and that must be 1. So I hope our tables look the same. Did I screw up?
Yeah,
I
you
times
just put
I is 1.
I'm so lazy and stupid on top of it.
minus
What did I
ones.
do wrong?
Your like furthest corners are -1 instead of -I. And then I think that
Dang.
screws you up somewhere else.
The furthest bottom right is
-1.
Thanks.
Yeah.
Yeah. Is that it?
Top corner too is -1 right now.
Top corner, be more
Top right
precise.
corner.
Thank you. Is, oh, minus I. Got it. Thank you. Better? Wow, that's pretty sad. That was supposed to be easy. That's what happens when you get cocky. That'll do it to you. So I was thinking, Penelope, if you're ever talking about things you like or don't like, about things in school, frame them differently. Like, it has been so helpful to me to have Fridays to work on other things. Don't play into the everybody's a lazy sack of shit mindset.
Well, I started, no, it was so funny, because I was like, I think I'm the only one in my friend group that has a Friday class, and that's how it kind of started.
Oh, God.
Yeah,
But just, you know,
yeah.
if we work together, we can build something. So, just another example. Here's a subgroup. This is a group unto itself. It's got inverses. It's got an identity. But this is just a lovely little subgroup unto itself. And there's other subgroups, but we're not going to get into them. Let's talk about how you verify that you have a subgroup. Besides looking at the group, dealing with the whole thing, which may or may not be emotionally possible because it might be so big or just incomprehensible, we want to have a subgroup test. So we have 2 subgroup tests. Subgroup test, we'll call this number 1. This is proposition 330 in our book. So it goes something like this. Suppose G is a group. We always know that we have a group and some subset of that group. H is a subset of G. Then H is a subgroup of G if 1, the identity of G is in H. So you've got a group, got a subset of it. We want that identity in the subset because we're not going to create a new one out of whole cloth. It's got to be the same identity as the original group. 2, if H1 and H2 are in H, then their composition is. So it's closed. H1, H2 is in H. That was kind of what we were verifying with our Cayley table of 1 minus 1, I minus I. Those were the only things that appeared. We never left that subset. And then 3, if H is in H, its inverse better be in there. Then H inverse is in there. And if this is the case, we have a little group. What is not listed here? How does this differ from the group axioms? We got closure, but we need that in the group too.
Doesn't have associativity.
Associativity, but why would I have that?
You assume that you're like a subset of G under some operation, then you assume that the associativity still holds under that operation.
Exactly. So if we've got this big group, big set G, and we know that we have closure there and associativity here, and I take a little subset H, well, the stuff in here better associate than if the stuff out of the whole group does. So it's in that same way. Oh, the integers are associative, so waving my hands. So associativity comes from the associativity of the big group. Let's just put a little note. Associativity comes from G, and it doesn't need to be checked. So that's just one little slightly less thing we have to check. Otherwise, it's just the group axioms on a little subset. We've got a second test. This is probably the one you're gonna wanna use most. There's like a compact version, but in the end, the compact version gets you doing all this shit anyway. So let's talk about it. But
For that second
yes, sir.
one, was one of the sets supposed to be G? For like if H1 and H2 is an element of H, then H1 to H2 is not.
No, because we already know that G itself is closed. I just want to make sure that if I take two things from the subset itself.
Oh, okay, I see.
Does that make sense? Yeah, I'm glad you're asking though. Yeah. Any other questions on these before we, yes,
I'm
ma'am?
so confused by that. Can you finish? If H1 makes sure I'm H, then.
H1 times H2.
Okay.
Oh, yeah,
I know
gotcha.
information, but I wasn't sure.
Yes. So we assume, right, you've got this big operation on G, it's got the little whatever composition. We use that same operation on the H.
Yeah.
They're
I
great.
wrote it down as multiplication, but I just wanted to make sure.
No, that's good. I'm glad you asked. I should have made that clear, so thank you. Any other questions? These are all awesome questions, very clarifying. So subgroup test 2, if there aren't any more, subgroup test 2 says something like this. That if H is a subset of G a group. So that means subset there. It's starting to get a little too pointy. Then H is a subgroup of G, so I'm using that notation now. If and only if H is non-empty, gotta have something, and G and H in H implies GH inverse is back in H. It's a one-step test, 2 steps. Make sure you're not empty. Second step is take any 2 elements out of there, and the composition of one with the inverse of the other better be back in there.
So you're saying if H is a subset of G and G is a group, then H is a subgroup of G?
Yes. So H is a subgroup. Yes.
But you can also use notation of the line under the subgroup
Okay.
and it means the same thing?
100%. Yep,
So
we do
the
this here like
The
that.
only defining difference is whether it's curved or point. Curved is subset,
Yes.
point is subgroup.
Yeah.
Okay.
Point is where we're assuming algebraic structures. The other one's just like stuff.
Okay.
Stuff inside of other stuff. So let's see if we can prove this somewhat casually, but walk our way through it. So let's do a proof. Let's do that direction first because that's easy. Assume, we're just going to assume H is non-empty because it's just silly to assume otherwise. Assume H is non-empty and that H is a subgroup of G. So I'm assuming this and I want to prove this. Take G and H in H. How do I get here? Let's see if we can walk through that. So thinking about, we know this, right? We know that it's a subgroup, so we have all these things we can do. How do we get GH inverse into H, like very methodically?
can't we use the laws that we were talking about
We can.
on
Yeah.
Wednesday?
Yeah, so how do what would be the first thing I might invoke?
I don't know, I'm thinking something with the identity element, but I don't know why.
So we don't need to worry about the identity per se yet, that'll actually be going this way, but what do I need? I need to get H inverse back in there.
Mm-hmm.
How do I know H inverse is back in H?
H times the identity element.
Look over here. We know these things.
So if
Oh.
we know H is an H, then we know the inverse is an H.
Wait, so are we already assuming that H is a group
Yes,
itself?
we're assuming we're doing
Oh,
this
okay.
direction.
My bad.
So, it's all good, it's all good.
Fair
It's
enough.
easy, yeah, let's keep our bearings.
So then according to the first test, if we're saying that H is in H, then H inverse has to be in H.
Yes, yep, so since H is a subgroup, H inverse is back in there. So why is GH inverse back in there? Thus, GH inverse is in H because what?
If H1, H2 is in H, then multiple candidate then is.
Closure. Yes, exactly. Because the product of any two things is back in there. Because closure under operation. And so that's like number 2 over there, right? We could even make a little, let's see here. So this is number 3 from over there, and then this is property 2 from over there. So that direction is pretty chill. If you have a subgroup, you can find inverses and you're closed under products, and so you're back in. So that one's done. The other way is more interesting.
Is that one also a proposition in our textbook? or
It is,
will we
it
always see
is proposition 3.3. Oh wait, can't be, must be 3.3.1 or something. I wrote 3.3 here, but it can't be, they both can't be that, so how about we just put 3.1
That works.
until I'm proved wrong. So let's go the other direction, because that is a little bit more interesting. So now we're gonna assume H is not empty, and this holds. And we're gonna prove we have a subgroup, and we're gonna test these 3 conditions of a subgroup. So now, the other direction, assume H is not empty, and that G and H in H implies GH inverse is back in H. What do we need to show H is a subgroup? So let's put it up, need to show H is a subgroup. So we can use test 1. Use test 1. What do I need?
Identity, closure, inverse.
Yeah, put them up here. Check. Identity. So it's E, element of H. Closure. GH and H implies GH. Product is an H, and inverses. Those are the 3 things we gotta check. We don't have to do them in any particular order either. But it might help to, how do I know the identity's in there? How do we get that?
Just, oh, because H is not empty.
Yeah, that's good. Okay, so since, I like that, H is not empty, what?
Oh, I guess.
No, you're so right.
Well, I was gonna say if H is not empty and it is a group first, then it would have to have an identity element, but we didn't assume that it's a group, so.
Yeah, yes, yeah, we're gonna prove that.
Yeah.
So we don't, how do we get the identity? But this is a key, there's something in there. So there's one thing, so there exists some H in H. So there's some critter in there. How do we get the E critter from our condition?
You multiply, you could do, G or H by its inverse, but you already know that,
Yes.
if H is an H, then you know H1 has to be, or H inverse has to be an H, and since H times H inverse, that would be E. So
Yeah.
it has to have identity.
Beautiful. These don't have to be different. This says no matter what two elements out of here, this has to be back in there. So what if they're both the same element?
That's the identity.
And that's the identity. So if G and H are in there, let's see if we can write this out nicely. So there exists some H in there. So by hypothesis, I don't want to write H comma H, but we can use H in place of the G and H over there. So use G equals H and H equals H. I kind of like to notate that. Does that make sense? That I'm replacing, and here another way to think this is this. And I'm just putting H into both those boxes. That if I take anything out here and I compose it with its inverse, it's back in there, or with the other inverse. So here we're going to have, by hypothesis, H comma H inverse is in H, but H inverse is E. So that's how we get the identity in there. Christian.
The by hypothesis, like proof technique, is it just like, what if, like, this were to be the case, like?
Oh no, so I mean by this hypothesis. But, so I've assumed that I have this rule up
Okay.
here, and so that's my hypothesis that I'm thinking of in my head anyway.
Okay, if you had like the stipulation that G and H were not the same, would you still be able to prove it's like, that we have a subgroup, like? You wouldn't
No,
be
that
able to,
would, then it wouldn't work.
Okay,
Yeah, this condition up here is, there's no restrictions on what those two things can be, so they can be the same thing.
okay.
That's kind of the
It's
crux
like-
of getting E in
Okay,
there.
yeah.
So now we've got, let's actually do, let's see, the second one. Let's do inverses next. So how do we do inverses? So this is, first thing here, we're gonna check, is E in H? And we just tested that, yes. 2. I think I put closure next, but let's do inverses. If H is an element of H, then H inverse is an element of H. And we're testing that. I don't know yet. I'm putting a question mark there.
Do you not already have that H inverse is an element of H from like the?
Well, I only know composition is, right? And let's put this back up. I know that if I have two things, then they're inverses, but I don't know that just that is per se. But I do now know that this is in there.
And you
Now, so what was that?
But you know that H times the identity element is the inverse of.
Yes. So what could I let G be up there to say the thing that I want to say here?
The identity?
Yeah. So let G be replaced by E, right up here. We already got it, right? And we have to build this in the right order. We have to first get the identity. Then, by our hypothesis, let's put this in again, by hypothesis, GH in H implies GH inverse in H. So let G be the identity, and you've got it. Then, H in H implies identity times H inverse is in H. Am I being too sloppy there? It's a little sloppy, I could've, Sophie's telling me I'm too sloppy, so.
It just, you're definitely, like, I guess in my brain, leaving the person reading the proof to assume that they know that
Yes.
each times the identity.
You are correct, my friend. So, keep this up long enough, I won't remember the quiz, but I'm still remembering it.
I'm not
No,
doing
I know you're not doing this. I know. I know. Let's be slower. Let's let G be in, so, we have E and H and H. And that implies EH inverse is in H, but EH inverse just is H inverse. So, H and H implies H inverse in H. Does that feel better, Sophie?
Yeah.
I agree. I didn't even like it before. I was kind of like, that's pretty shitty. What's my big rush besides giving a quiz? Quiz where I ask you what the definition of a group is. So, all right, so how did we feel about that? We have one last thing. Finally, so now we have to do closure. We're going to show that if I take G and H in H, then G times H is in H. How do we get that? Take a minute, think about that. You've got what you need in the first two steps. Yeah, what'd you think? Yes, it is something like that, very much, yeah. It's all good. You got it? Let's see, wait, so assume G. So where are you using, oh wait, so what is that?
H inverse.
H inverse. I think that just gets you your identity back. So I don't think you're getting closure, I think you're just getting the identity.
Okay.
I think you did the identity proof perfectly. Bless you.
Thank you.
What's that? What is that? What is the inverse of H inverse?
Isn't it just H inverse?
Well, what do I multiply by H inverse to get the identity? Because that would be H. So, since H is equal to H inverse inverse, and I know that this thing is closed under, wait, so, oh shit, now I gotta get it pulled together in my head. So, GH is equal to GH inverse inverse. And this is already in there because I know that it's closed under inverses. So H inverse is in H by R2 over here. Wait, isn't that right? Yeah. So we already showed it's closed under inverses. So this is an element of H, and I'm taking its inverse, and so that is an element of H by hypothesis. Remember that the hypothesis, it's throwing you off, and I know why, But it's saying this, that if I have two things in H, then this, I have to just make sure that's in there. And so I'm putting H inverse into that little bucket. It's a subtle way.
Your H is now H inverse.
Yes.
So,
Yeah.
how does that prove? Cause didn't you do then that G and H inverse in H implies G composed with H is in H?
Say that again.
So your closure requirement
Yes.
is G comma H and H, but you used H inverse instead of
Yes.
H.
But I wrote H itself in terms of H inverse because I've got this rule that allows me, the only thing I can assume, Cormac, is that if I've got two things in here, then this is back in there. So I'm saying instead of using G and H, what if we use G and H inverse? So I picked G and H. I already know that H inverse is definitely in H by step 2 over there. So I might as well just pick that. And now I'm using H inverse as that H. And so it's inverse just gets me back in there.
Okay.
So when you're doing like proof by hypothesis with like this, I think the thing that's tripping me up is
Yeah.
the fact that like we keep changing what G and H are
Yes.
throughout the whole thing. You're
Correct.
able to do that.
Oh yeah.
It's not just for some G.
No, it's for all. So this was for all. Any two things in that
I
group.
think that.
Yeah.
Absolutely.
And I knew that was the part. That's why I've been trying to draw this little boxes, because I think that this definitely helps.
I think you would. Yeah. I was just getting caught up on.
No, it's and I knew you would. That's why we did this. It's tricky. It's subtle. There's no big moves, right? It's all just like, oh, this little tiny thing has to be observed, and then we tweak our way there.
Yeah, I think the thing that's hard about it is you're just manipulating the sentence basically what you want. And it's
Exactly.
hard to
It is.
wrap around.
This is hard. Yeah. So we okay? Yeah, right, yeah, we'll find out. So Wednesday, we're gonna work. I might start off with like a few things, but it'll be primarily a work day. So it wouldn't hurt to look at the problems before you showed up on Wednesday. Just like, oh, there's my book. Okay, I'm done. You know, even that, just like pick up the book and press it against your head. Anything that takes that book and gets those problems closer to your mind. Please? Question or just?
I don't know, it's
Just like, yeah, good. I'm almost like, I'm tempted to make I'm working on the dance from Touch, the Cat's Eye song. Do you know the song I'm talking about? Touch, touch, touch.
Oh,
I may show you guys by the end of the semester. That'll be my gift to you, yeah.
Yeah.
And then we can all do it together and like just get in line and be like, little cat's eye in here. Okay. Anyway, I didn't forget, could you please take a piece of paper out? I almost
No.
forgot, I almost fucking forgot.
it's gonna take you more than 5 minutes, guaranteed.
It's not gonna, well,
So
I mean, if you become a weirdo about it, but I mean, you might